Whoops, that's not what we want. That one. So when I was putting this together, and you'll see the title says quantifying or soil carbon quantification and chemistry, and when I had half an hour to talk, there's no way I could fit both of those in. So contrary to what Ron said, you're not going to see an NMR spectrum in this talk, which is probably one of the first times I've ever done a talk without one. But what I'm going to look at is basically, I want to run through a couple, how we go about quantifying carbon in soils and some developments that are happening currently within the emission reduction funding. So first of all, what are the requirements? Secondly, I'm going to talk to you about a project that we've just finished up, measuring temporal variations in soil carbon stocks. There was a lot of surprises in it for me, a few things that I hadn't expected. Talk about how we go about developing and optimizing these methods for quantifying stock, and then a little bit about what's going on currently, and I'll try and finish up with a summary of it all. You've probably all seen this from me before, or potentially you have. How do we measure soil carbon stocks? And you need to sample. First thing to recognize is when we talk about soil carbon stocks from a carbon accounting framework, we're really dealing with stuff that's less than 2 millimeters. We don't count the big stuff because we think it decomposes so fast it just brings volatility into the accounting, so we don't count that. We have to sample to a minimum depth of 30 centimeters. That's for consistency with our national greenhouse gas inventory. You can go deeper if you want, but you need to go to 30 centimeters. We need to know the bulk density. We need to separate out the gravel and measure the content of stuff that is less than and greater than 2 millimeters. We've got to get the carbon content of that material, and we've got to run some equivalent mass calculations, which I'll talk about in a minute. And then with all of that, we can put it through this formula and come up with our carbon stocks. One thing that, and I'm guilty of this when we started the soil carbon program, the bulk density question always comes up. Measuring bulk density, we've got to be so careful about getting that exactly right. And I would now say, after running through the carbon program and the work we've done, if a sample's not good enough for bulk density, it is not good enough for carbon. And this idea that you can take a grab sample for carbon, then go get a bulk density number, or be very careful about your bulk density sample is not correct. If we want to know the carbon concentration in a layer, we need a nice equal representation of all the depths. We need to mix it all together well. We can't say we're going to take these cores for bulk density and do them really carefully and then back off on how careful we are about our carbon, because it just won't work. We need to have the same care in taking the carbon sample. So, given that, this challenge that everybody thinks about getting bulk density, if you do your sampling carefully, it should be fine. You need the mass of soil in a defined volume. And that's the key. Get your volume defined, take all the soil out of that volume. You need all of it for the carbon count too, to get the carbon measurement right. One of the things that happens when we're measuring carbon through time is the management practice might induce a change in things like bulk density. And if you keep sampling to 30 centimeters all the time, you're going to introduce error. So people have come up with this idea of expressing the variations in carbon stocks on the basis of an equivalent mass. And I just want to run through that so that people that might not be familiar with it understand why we use equivalent mass. I'll then show you in this experiment, or these trials that we ran, how important it actually is and what difference it makes. So here's our reference state. We've gone out at time 0 to do our baseline sampling. We've sampled to 30 centimeters. Let's just say through time now we're going to go back at some time in the future, T1, and sample it again. But let's say that management practice has induced a compaction in the soil. So the surface is now a little bit lower than it was before. If I go in and sample to 30 centimeters, I'm actually going to sample a depth X of soil that I never sampled in the first place. That's going to be in the bag. That's going to get counted. Any carbon in that then will also get counted. So you could say a management practice could come along, compress the soil. I measure to 30 centimeters. You could end up measuring a higher stock when in fact there shouldn't have been one. So what we really want to do is just count the carbon that's in to the same depth. Now that's got the assumption that any changes in compaction and bulk density have all occurred above 30 centimeters. If the compacting is happening very deep in the profile, then what I'm saying probably goes out the window and you've got to think about it even more. The next thing is, well, what happens if you fluffed up the soil? And again, if we go and sample our 30 centimeters, we're actually not sampling the whole volume, the whole mass of soil that we sampled before. And what we really want to do is sample all the way down to there. So if we, instead of basing our sampling on a volume basis, we base it on a mass basis, we can take care of this. And just to run through that, the big problem that's associated, or a problem associated with all these equivalent mass calculations, is soil carbon content changes with depth. So we've got depth on the y-axis, carbon content across the top. If I go and I sample, my applied practice has come through and caused the bulk density to increase. I'm coming along and I take my soil sample. I only want to take this much of it because we know it's increased, so my mass that I need to sample is less. So what I can do this mathematically, I can just discount the bottom of the core. But if I've done it in one push, I've put all this high carbon concentration soil, I've mixed it up with this low carbon concentration soil, and I'm actually going to discount it too heavily. So an improvement on that would be to go and sample layers. And instead of knocking it off for the amount of carbon, the average amount in the whole profile, I just knock it off for the average amount in the lower layer, which by the time we get down 30 centimeters is typically stabilized. So I'm not going to cause as much of a perturbation to what I should actually be measuring. Equally, if the bulk density has decreased and I need to go deeper, I can take my if I worked off one profile, I'd be probably putting way too much carbon in. If I'd taken these, I can fix that by just using the carbon content of that layer. And even better is to sample one layer beyond which you want to do your accounting to, and then you can cover all bases. And you can put that soil back together with the mass you want, with the best carbon numbers you can. So that's the equivalent mass framework. What I want to do now is go through some results we got out of a temporal variability project that we've just finishing up. It had two components. It had an intra-annual variation, so we looked multiple times through the year. And this was a Filling the Research Gap project funded by the Department of Agriculture. We went to 5 different sites listed here. These were all research trials. They all had 4 replicates in these research trials of a particular treatment. We picked the treatment that we thought would have the biggest variations through time in carbon content because they were growing the biggest biomass. So one of the questions we were looking at is, if we sampled in peak biomass, do we get a higher carbon value than if we sample outside of the growing season? So they had 4 reps. We sampled all of them. We measured the layers, carbon contents in the layers, the bulk densities, everything needed. We calculated the carbon stocks of 0 to 30 centimeters, and we calculated them on the basis of an equivalent mass. Different soil types, different management regimes, different crops in place across those. I'm going to show you the data from a couple of the sites. So what we've got here then is the carbon stock against the days since we collected the first sample. So it's roughly 2 years and roughly spaced out monthly, usually somewhere between about 20 days and 30 some odd days separating. The first thing that blew me away with this is the size of the variance that you see going from month to month to month. So in some instances, we've gone from, say, 82, 83 to 92, 93. We've had a 10-ton change, 10 tons of carbon per hectare change over the course of a month. That's just, from my understanding, it's not biologically possible to think about that much carbon being dumped into it. So there's got to, and part of the problem here is that we've got a whole pile of sources of variation that we're trying to deal with. There may be a true temporal underlying trend through that data. We've got spatial variation. We've got differences in sampling. Did they actually get to 30 centimeters, or did they get 30.2? Or did they get, did the cores compress a little bit when they took these samples? The preparation, were the samples well homogenized, or were they not? And therefore, is the little bit, the 1 gram or 2 grams that we put in our analyzer actually representative of what was in the paddock? We can do, and I should say, it was when I first started in the carbon accounting stuff, people were standing up and saying, we've measured 2 years ago and we've measured again now, and we do the calculations, we're saying in 2 years these systems, or this particular paddock or this system, has gone up by 10 tons of carbon per hectare. And we'd say, well, that can't be right. There's got to be a problem with the data. I guess what this has showed to me is one of the big sources of error that's going to happen in this, or uncertainty. And yes, it's possible for a farmer to go out and sample his paddock now and go out and sample it in a few years and get these kind of numbers. But the problem is that it's not necessarily a true temporal trend, because there's all these other sources of variation in it confounding it. If we do the equivalent mass calculation, that actually takes care of any spatial variations in bulk density and depth and all that sort of stuff. That gets rid of all of that. And what you can see is things tighten up. So if the crew that had gone out had sampled it perfectly, the last graph would have looked like this. It still doesn't deal with the spatial variation in soil carbon content. It doesn't deal with the temporal trend. It doesn't deal with preparation and analysis. But it does help stabilize some of the variance that we would see due to the way the soils are actually collected out of the ground. So this particular one's at Armadale. The next thing we can do, if we want to try and get some idea, is there a temporal trend, is on the assumption that the variance about a regression line is due to the spatial and the way the samples were prepped. If there are a true underlying trend, we can try running a linear regression. We could try running some other types of lines. At this stage, this one is using the linear regression. We can get a slope, which is basically telling us at this site, we would say we'd be getting 4.2 kilograms of carbon per hectare per day over those 2 years, a positive change. And if you convert that into tons per hectare, it's looking at 1.5 tons of carbon per hectare per year with a standard error and a known degrees of freedom. Now, I'll come back to that, because we want to use that then to tell us how confident we are in those numbers, so that a farmer or a landowner doesn't just get a single number and trade on that. They can get a risk strategy together for doing it. So this is what we got at Narrabri. Narrabri is a vertisol. It swells, it shrinks, it cracks, it's irrigated, and that's the variability that we saw. On the order of 20 tons of carbon over a few months, over these in here and in here. And those sort of things just shouldn't be happening. But when you think about how difficult these kinds of soils are, look what happens when you run the equivalent mass calculation. So in this case, the majority of this variability we saw in the last slide is just due to the fact that these soils are a bugger to sample. They swell, they shrink, they compact when you sample them. To try and then get any reasonable measurements through time is tough until you start to invoke this equivalent mass calculation. At this site, again, it had a positive slope. It was going up, and 1.62 tons of carbon per hectare with a standard error and the degrees of freedom. Now, what we want to do then is use this kind of information to tell us something about the probability of what's going on. And I can take that standard error, that slope, and now we've got the slope on this axis and the cumulative probability on this axis going up. So that just tells me, based on those numbers, assuming normality, what's the chance of certain things happen. So I could, the mean, that 1.62, I think it is, if you went off across at 0.5, would drop down to here. The other way is just tip this curve around the other way and look at the probability of exceedance. So if I was a farmer and I wanted to be 80% sure that I'm going to enter a carbon trading game, and I want to be 80% sure that I've actually got those carbon stocks, what you do is you come up to the 0.8, track across it and come down, and that's the value that you'd enter into your carbon accounting. If I was a real risk taker and I wanted to get all the money I could and I didn't care that it was only 20% probable that it happened, I'd come down to the bottom here and I'd go across. And what you can do then is use that graph to get an idea of what the riskiness of putting a certain amount of carbon into a carbon trading account would be. Okay, and just one other one I'll show you. This is the equivalent mass for a site at Camden. In this particular case, this system was going backwards on average. So the trend line in this case went backwards. I just threw this one in to make sure you realize not everything is going up around the place. And it only went up over the 2 years. So the next thing is, we don't know if that was a trend that's just due to the 2 years that we've had, or whether that will be sustained. I guess the important thing is that once you get lots and lots of points in your regression, you can start asking intelligent questions about it. Sorry, there was one other thing I wanted to say back here. Many people, and so this might be the farmer's paddock that I talked about before. are just taking 2 points in time. And how do you know what really has gone on? If I could get any result I wanted by just taking 2 of those points in time. So we've really got to, as we build up and think about being certain about what's going on in these things, we've got to get multiple temperature measurements into it and start looking at trends. Okay. The other thing that was done in this project is some colleagues at University of New England went back and revisited some sites that they sampled 5 years previously. The sites were all in New South Wales. These are the sites. They comprised mostly grazing. They had some cropping and some native woodlands. For those of you that are interested in soil types, those were the soil types that were sampled. In this case, they sampled one more layer. They sampled a little bit more, in a little more detail at the surface, but all the way to 30 centimeters again. And in their case, the MER program was set up to a 25 by 25 meter piece of ground that was geo-referenced. They put a grid across it. I think they were something like 2 meters, 2 meter grid, and they allocated each of those points. And in this case, they've sampled 10 cores to the 30 centimeters, and then averaged the data after the analysis. And here's the results. I hope that's fairly discernible, but rainfall is the light blue color underneath. The main point that I want to get out of this is some of these soils dropped, some of them went up, and there was just no trends in this. Across the managements, everything. When you plot the 2008 numbers corrected for equivalent soil mass against the 2013, there tends to be, across the whole data set, there was no significant change. It's almost a one-to-one relationship with the slope of 0.95. The stock did increase at 6 sites, and it did decrease statistically at 11 sites. The range was everything from minus 32 to plus 32 tons per hectare over 5 years. And again, I think, and it's harder to understand how spatial variability creeped into this one because it's based on 10 cores taken out of a 25 by 25 meter grid. So maybe it's not just spatial variability. Maybe some of the other things like plant growth or variations through time are creeping in. Maybe erosion happened on some of them. I don't know. But just to say, the variance that we see is pretty big. Okay. In the few minutes that's left, I want to move on a little bit to look at what people are doing now, what the methods for estimating soil carbon and carbon stock change are, and this stuff's been funded by Department of Environment and GRDC. So when we want to monitor change through time, it's a couple principles. We've got to consider the whole area. We can't just look at part of it. We need to come up with some idea of the uncertainty or certainty associated with the stock change because we want people to trade on an understanding of what the riskiness of what they're doing is. And we want multiple measurements through time to detect the trends. And there's all kinds of methods ranging from something that's measurement-based, where we might be going on through time, taking measurements, and we're actually calculating retrospectively what the change is, through to predicted, where we're using projections based simply or solely on modeling. And actually we have, and I'll say in a minute, we've got both of these methods in place in Australia now. So here we've got measurements at multiple points of time across the entire area, and we define a temporal trend. Here there is no measurement. The change is based solely on an evidence base of the impact of the practice. And when you look then at what comes out of this, basically what happens is the confidence in the magnitude of the change at an individual point decreases, but over the whole area, if the area is characterized by huge spatial variability, if you're able to get a certain precision at every location, you might actually end up with an increase in the confidence, and I'll deal with that a bit more in a minute. And the other thing is the cost of data acquisition decreases. It's expensive to send people out in the field and collect heaps and heaps of samples and get them analyzed. If we could come up with some modeling-based scheme that we were certain of, would be very good. So in Australia now, there's actually 2 methods. There's a direct measurement method called sequestering carbon and grazing systems. It's operating, been there for about a year. Carbon was traded in the last auction against that method. In July this year, a modeling method came online. So both of these are out there and people are starting to use them. So carbon trading in soils is happening. I'll mention a couple of definitions. In this carbon trading game, they call it the carbon sequestration project, and that box represents the entirety of the area over which this project applies. They break that up into carbon estimation areas, CEAs, they call them. I've made them continuous here. They don't have to be. They could be separated by space. But the carbon estimation area is the place in which you're going to do your groundwork. And then what we're saying is inside each of those areas, you break it up into different strata. And then you'd be measuring carbon by compositing across the strata. So in a minute, as I go through the next slides, I just want to make sure everybody had an idea of what a project was, what a CEA was, and what the strata were. It doesn't have to look like that. It can look very different from that. So the first method that's out there now, this direct measurement method, was designed to be used anywhere with no prior knowledge of spatial variability. It really just represented a starting point. You don't have to separate it. You just put your strata, equal area strata, down on a field. And the way it basically works is the purpose is to detect change over time. In this particular issue, we've got 9 strata with 3 composites. And what basically happens, that's one of our composites. So we've taken a core from each of the strata, put it in a bag. We've collected another composite and another one. So now we've got 3 composite samples from the 9 strata. So each composite has 9 cores inside it. The reason we've done this is the spatial variability, although not measured, is inside and encompassed in every one of those samples. If I'd have sent all those samples to the lab, the spatial variability would be in the variance that I'm trying to use to detect the change through time. What I've done is buried all that inside the sample so that when I get my numbers back from the lab, they'll be a lot closer and the variance will be a lot smaller, and my ability to detect change through time will be greater. So then I'd go and sample again using the same sort of protocols, and again using the same sort of protocols. And what will happen with this then is, hopefully, the minimum detectable change is small enough if you put enough composites and strata in place that you'll be able to claim a certain amount of carbon. There are other methods. I'm going to just really briefly go through them. There's a couple that are being looked at. Raphael Vizcarra-Russell, a colleague in Canberra, is running a little buggy with some sensors, a gamma sensor and an EM sensor on it. He goes through and he maps out the different areas of soil properties, not necessarily saying they're related to carbon yet, but soil properties. He can then, on the basis of that, go and collect some cores, hopefully then get some additional information around climate, topography, tie that in with the measured values and come up with some models that might allow him to be able to predict carbon through space. Now, if the spatial variability is starting to go up, this thing can go over the whole area. We're not dependent on such small little sample sets. We can take this the next level up and go to something like remote sensing. It's basically quantifying the vegetation cover. It's got complete spatial coverage. Resolution might not be quite right for some small scale projects. It might be great for farms out in the rangelands. And it provides an indication of carbon inputs, and it's probable that there's some relationship between the amount of green stuff on the surface and the amount of brown stuff in the ground. And that's what we want to try and get some idea of. So to come along again, you get some ancillary information to go with it. You try to build a model. If you're successful, you can generate a prediction across the whole space. Now, you'll notice, hopefully, on the last slide, the error size here. I've purposely made the error size here a bit bigger because I think it will be a bit bigger. The real key to all of this then is we've got these different methodologies. The accuracy of the methods across them are going to change. However, these methods give you a lot better spatial representation than going out and taking cores. So what we really want to get to is, first thing is, we got to know what the true uncertainty is about each method. And the second thing is, once we know that uncertainty, at what level does spatial variability tell us we need to jump to a less certain method? So where do we sacrifice analytical certainty to get complete spatial coverage? And there's got to be an optimum where those things are going to cross over. We don't know that yet because we haven't even defined all the uncertainties associated with these methods. But just an example, I would never recommend someone in the rangelands to try and use this sort of methodology to quantify the carbon stocks on a 100 kilometer square property. Because we wouldn't get it. There's too much diversity. It'll cost too much, and the carbon change won't be very big. But if we can develop algorithms, even with an analytically a higher uncertainty, but we get complete spatial coverage of a very diverse environment, we might be in a better situation than sending those few cores out. And maybe we do send a few cores out for calibration and validation purposes. The other methodology that's currently in play now is modeling. Basically, we take, it's built on the NCAS system, the National Carbon Accounting System. The sources of uncertainty here are quite large as well. The initial stocks, how much is there, what are the model parameters, and how certain are we of them, environmental data. We can do things like input project-specific values and maybe tie in that first point so that we can model forward from something known rather than modeling forward from something that's thought. We can use national default values if we wanted. Right now, the system has been set up to use national default values and to basically create, I forgot the name, to create, not enrichment factors, just a factor that describes the carbon change. What the heck they call them? Emission factors. So they've set it up, and they've said if you can invoke or show that you can accumulate or put more carbon back in the ground, grow bigger biomass, they've done the modeling, and they've said you will get an emission factor, and an amount of carbon will be sequestered by increasing your biomass production. The nice thing about the modeling, which is different and worth noting, is that in our measurement capabilities, we'd basically go take our T0 value and we'd measure through time, and we are only going to be allowed to account for sequestration. Because in that scenario, we have no idea where the business as usual case would have gone. In the modeling scenario, they can model through the business as usual and model through the new management practice, and they will be allowing trading on both the avoided emission and the sequestration if that happens. So, summary. So, spatial variability, sampling issues, sample processing and analysis contribute to what I've bolded and underlined here, something I'm calling an apparent temporal change. And it's really important to recognize that if I just have two measurements, the certainty associated with the value off those two measurements is going to be pretty low. We can invoke the equivalent mass calculations to help, but it doesn't solve all the issues. We really need to get these multiple temporal samples in order to detect what's the trajectory and where's this thing really headed. Methods have been developed to allow accounting of carbon. We've got a direct measurement methodology using equal strata with compositing and regression. We will be going forward, hopefully, in developing other methods where if I had some prior knowledge about how the soil varied across a CEA, I might break it up into 2 or 3 different CEAs to respect those soil boundaries, or I might use those soil boundaries to define my sampling strategy and change it from what I've shown you here. But what I've shown you here was put together as a base, an entry point for anybody to get started in it. The modeling is online. It's essentially an emission factor approach based on practice. There are huge uncertainties that have not been quantified in it, as far as I'm concerned. And that's a place if we really want to go forward with that. The reason, I guess, I can sleep with the fact that we've got that is the government's bearing the risk. There's no verification required from the farmers other than that they have implemented the management practices. There's no auditing to go back out to the farms, so they're basically, it's a payment on practice. And they assume that the modeling tells us the right change. Quantifying the certainty associated with these different methods is really required, and I'm sure we should be bouncing from method to method as a function of the site characteristics. And we really need this analysis to optimize where different methods are used and I guess match them to the land characteristics that we're looking at. Or that, sorry, not that we're looking at, the land characteristics that are in place in the places we're trying to monitor. And that's where I'll finish. Thanks.
Interesting talk.
Yeah, man.
I've just got a quick question. For the temporal project, did you work out a time that was best to take samples from?
No. We tried. I think spatial variability is killing us, basically. The variance that there's so much variance in the data that we did not see higher values at peak biomass, for example, versus the when there was no plants growing. There's a little bit in it, but nothing significant that we can, say, go do it. I would still recommend anybody going to sampling carbon, though, to sample at the same time of year each time. It just seems intuitive that it should be there, but because of the spatial component, I think we haven't been able to find it. Ron?
Continuing on from that, in these systems, what is the ratio of soil carbon to biomass carbon standing?
Can't tell you off the top of my head. I'd have to look at that. To stand.
So the only reason why season would matter is because the amount of biomass that you're producing each year is, and the amount of that goes into the soil is.
So yeah, I've done that. That's a good point. In let's say a Mallee system, I can do it quickly. A Mallee system that's growing 1.5 tons of wheat probably got an equivalent amount above ground and below ground. So say 3 tons. So 50% carbon, 1.5 tons of carbon going into a stock of maybe to 30 centimeters, 30 tons at the most. So it's not insignificant. Yeah. And as you move into the higher production stuff, Hamilton, they're growing 6-7 ton wheat crops, if I remember the yield stuff right. So if you work the numbers out, the number's big, but it's a flux, right? There's as much coming out as there is going in. So, but it's worth worrying about. Wayne?
Jeffrey, what's the, if you look at the analytical, just repeat the same sample over time, what sort of size does that come up?
It's about, at worst, about 1%. Yeah. If we put the same sample in, provided it's been homogenized right and all that other stuff is done right, if we put our 2 millimeter stuff through the carbon analyzer repeatedly, we're usually less than 1%. 1% would be the top. So I think we can all, that's for the LECO. If I now go to MIR predictions, of course, there's a higher uncertainty because I'm no longer running it through and getting the direct measurement of carbon. There's an error associated with my MIR prediction. So that depends a little bit on the methodology, but if we're using the LECOs, it's pretty tiny. Probably doesn't even need to be considered.
The reward for doing this is that potentially soils can store a lot of carbon and can be brought in sequestration mix overall in terms of what we do for climate. That's why we started this, and that's why you'll pay to start this. All this extra data surely has improved your idea of what the potential is. So you kind of started, it could be anything from this valuable to 100% of our emissions. Have you got a better idea of what kind of, how much carbon can you store in soils?
I'd be a little hesitant. I'll take that on notice. There's a couple of studies that have been done, one based on modeling, which has said if we could grow at 100% water efficiency wheat year after year after year at locations around the country, what would the carbon carrying capacity of that soil be? And I can't remember the results off the top of my head, but it won't. There's two. The first issue is it will be something that's useful. And look, I would be saying build carbon for all the good things that carbon gives you. And if you can get a few bucks out of it, out of the carbon trading scheme, and you're willing to take the risks associated with whatever part of the carbon trading scheme you enter, great. But do it for all the other things that it does first. And I should have put it up in part of my summary. The challenge for us as scientists, because I don't think we're there yet, is to say if I build my carbon from 1.2 to 1.6 on a red-brown earth in Clare, what's my increase in water holding capacity? What's the impact on infiltration of water? What's the impact on delivery of nitrogen to the next wheat crop, so that I can figure out what the economics around the yield benefit is? Because too often I see the economics in this area is built strictly around the carbon change, and that's not right. If we can really understand the impact on the productivity side and add that to what the carbon sequestration program might give, then we've got something to give to the farmers.
All right, I think we should move on, but I forgot to mention we will have breaks and meals in normal locations at Charles School, so hopefully Jeff can hang around and people can bring up discussion with Jeff later on. Don't go too far through. You do get something out of this, but thank you for giving up the time.
Yeah, I'll let you do it.
Thank you.
Sorry.
First of all, I'd like to say that I was really thrilled to see that Renga got chosen as the first ever fellow of the Australian Soil Science Society, or Soil Science Australia, or whatever they want to call themselves. I think it's to the Society's credit that Renga was chosen for this. Of course I congratulate Renga, but I think the Society has chosen well. The Society has chosen a real scientist, and they've chosen someone who still enjoys, in fact he gets a great thrill, as I think we'll see, joining the dots. And someone who also bases a lot of his results, a lot of his conclusions on quite simple experiments. Well done, of course, and often done by himself. Now, they didn't choose someone who's a seeker after positions. They didn't choose someone who's a builder of research groups. They didn't choose someone who's always seeking funds. They didn't choose someone and meeting the right people, going out to meet the right people. And they didn't choose a nitpicker. Now, one thing I want to say about Renga is that he's got a great sense of humour. He usually tells a joke, an original joke before a talk. I don't know if he's going to today, no pressure, Renga. But I want to relate one that I remember. The late Ken Lee, when he was introducing Renga at the Australian Soils Conference in the early 1990s here in Adelaide, Renga at the time was working in Tatura, and Ken told us that he talked to Renga beforehand, and he said to Renga, "Are you the chief there?" And Renga said, "No, I'm not the chief, I'm just one of the Indians." and in fact, Renga's story begins very much in a very small village in India, in the south of India, and Renga has told me that this place was so small and so far away from everywhere else that he'd not even heard of, when he was at school, he'd not even heard of a university. He didn't know what they were. Of course, he eventually heard of the university. He did a degree in chemistry. He went on to soil science, or I'm not sure if I got exactly the right Renga, but certainly soil chemistry came out. Then he went to Belgium for a while, and then he came to the White, worked with Malcolm Oates. Then he went to teach in Tanzania for a while, and then he came back to Australia, to Victoria Department of Agriculture, probably at Tatura. And then Renga was one of the first appointments of the first branch of CRCs that were created. CRC for soil and land management. And he's probably one of the few that are still around. Now, Renga is a real expert in sodicity, as almost everybody knows, and we shall see. He practically invented the word. He certainly spread the gospel of sodicity widely among the likes of farmers. And it's my pleasure to introduce you, Renga.
Thank you, Doug. Now I know the appropriate person to write my obituary. Now, this dispersive soils all around the world, particularly in Australia, about 67% of the agricultural lands are affected by dispersive soils. As you know, this farmer is worried about this dispersive soil. Perhaps he is also worried about the lack of funding for soil research. How do you go? This one. Now, Dr. Bill Emerson in CSRO first developed this testing for dispersive soils. Now, as you know, that as you increase the exchangeable sodium in the soil, the dispersion, clay dispersion increases. It increases as usually in Australia we call sodic soils if the exchangeable sodium percentage is above 6, whereas in the United States and other parts of the world, if the ESP is above 15, it is considered as sodic soils. Now, instead of dispersive measurements, you can also measure exchangeable sodium percentage, which we call ESP, or sodium adsorption ratio, which we call SAR, as an indicator of sodic soils. Now, as you know, this is a field which we visited during Doug Churchman and myself and others went near Horsham during the CRC for soil management period. The soil after the rain is completely, the aggregates are completely destroyed, the waterlogging occurs, and as the soil dries, it becomes hard, the aeration porosity, hydraulic conductivity, everything is decreased, and indirectly it affects the crop production. Now, is this caused only by exchangeable sodium? I mean, all over the world, people are thinking that sodic soils as dispersive soils. But there are dispersive soils which can be affected by other than sodium. Now, not only in agricultural area, the dispersive soils are also found to affect landslides and building cracks and building collapse, sinkholes and so on. Now, when we worked on a project funded by GWRDC, Wine Corporation, to look at the effect of winery wastewater irrigation, we came across that winery wastewater contains a lot of potassium. In order to avoid the sodium in the disposal water or wastewater, they started using potassium hydroxide for cleaning the winery equipment. And because of that, the potassium concentration started to increase, and in some of the wineries, they found that the soils are affected. In fact, in France, over 30 years of application of potassium fertilizer has increased the clay dispersibility and decreased the aggregate stability. Now, this slide shows that keeping sodium constant, that is SAR at all tubes as 1.2, but increasing potassium adsorption ratio from 6 to 8.4, 11, and 15, we can see the increase in clay dispersion. So we identified that potassium can also affect soil structure by means of clay dispersion. Then this is a tunnel erosion, which is quite common in Tasmania. All these soils have very high magnesium in addition to sodium. So even in general agricultural areas, there is an opinion that magnesium is causing dispersive soils, like sodic soils. It was I think Bill Emerson and colleagues, Emerson and Baker papers, where they showed that sodium magnesium soils disperse more compared to sodium calcium soils. And from that onwards, there are so many reports saying that magnesium can also cause soil structural problems. Now, the major thing is the rainfall impact. The rainfall impact is considered to affect the soil structure. I was a visiting scientist in Malcolm Sumner's lab in the University of Georgia, where I was arguing with Malcolm that the reaction between water molecules and the soil, that's more important than the energy of the rainfall that is causing the clay dispersion and aggregate disability. Therefore, we conducted an experiment practically on the Malcolm's backyard, in his house backyard, but because the university didn't allow us to use other chemicals as a rainfall. So we did in the backyard having a big carboy of water, distilled water, about 30 feet above the roof, and then collected the samples of the showering of the water, just like a rainfall, and collecting the dispersed clay. When we used water as the rainfall, the soil completely dispersed. It is a highly sodic soil and dispersed heavily. But when we used diesel as the rainfall, the carboy full of diesel, and when the rainfall affected same energy of impact, but there was nothing. The soil remained stable. This indicated that the color here is not because of clay, it is because of the color of the diesel. It mainly indicated that the charge on the liquid, that is more important. Water molecules are highly polar with a dielectric constant about 82, whereas the diesel is non-polar. So dielectric constant is about 1.2. So the charge on the water molecules is responsible for the reaction with the soil. Soils are charged particles. So the charge-charge interaction causes the dispersion problem. Then we found that there are so many other factors causing the changes in the charge in the soil. One of the factors is the pH. If you change the pH of the soil, as you increase the pH from 6 to 8, 6 to 9 here, the clay dispersion increases. Whereas between pH 4 and 5, that is called 0 point of charge, the soil charge is 0. That means positive charge and negative charge are equal. So the net charge is 0. Because the net charge is 0, there is no clay dispersion. When you go to the pH 3, it attains positive charge. Whereas between 6 and 8, 9, the soil charges are completely negative. Whereas at pH 3, it is positive charge. Positive charge also can cause dispersion, and the positive charge, the effect is not because of cations like sodium or magnesium or potassium. It is because of chloride, sulfate, and so on. Then in another case, we checked soil from a border town. The exchangeable sodium percentage of the soil was about 19. And the air-dried condition, when the soil was air-dried and put it in water, it completely dispersed. When you heat the soil to 100 degrees, the dispersion was reduced a lot. Then about 200, 300, 400 degrees, there's no reaction was there. When you heat then we realized that when you heat the soil, the hydration charge is completely reduced. The hydration charge is not equal to cation exchange capacity. It is hydration charge is reduced. At that time, we thought that the sodium is combined with the clay in a covalent bond forming. Therefore, once they are bonded by covalent bond, the water molecules cannot react. Most of the organic compounds are covalently bonded. That's why the water is not reacting. Therefore, the solubility of non-polar liquids in water is very low. This is another, organic matter also affects, but there are so many different views. What we concluded was, if the organic matter is bonded to the clay in a covalent bond, then the hydration charge is reduced and the dispersion is reduced. Whereas if the organic matter in the soil is ionic bonding, free molecules with a negative charge, they will increase the dispersion. At the same time, some of the organic matter can be hydrophobic character. If the hydrophobic organic matter covers the soil charges, then the water molecules don't react, therefore there is no increased dispersion. The dispersion is reduced. This is an example of a Claremont soil which has a very high cation exchange capacity because of this magnetic mineral, but the organic matter is about 4%, and the organic matter is completely bonded to the clay in a covalent bond, and the clay dispersion is very low. the turbidity measures the clay dispersion is about 1560 NTU units, whereas Adbray soil, which is kalanitic and elatic, which has a very low cation exchange capacity, very low organic matter, but it disperses heavily. The charge reduction is also realized by the zeta potential of the dispersed clay. You can see the negative charge, minus 32 means negative charge. Claremont soil with the high cation exchange capacity has a lower zeta potential compared to the kalanitic and elatic soils of Adbray. Now that's why we base this hypothesis that if the cations are bonded to clays by covalent bonding or ionic bonding. This is a simple example. Sodium and chloride are bound by ionic bonding. So if you put it in water, completely dissolves, separates sodium ions and chloride ions separates. Whereas calcium carbonate is highly covalent. Calcium is linked to carbonate molecule by covalency, is completely mostly covalent. So if you put calcium carbonate in water, solubility is very, very, very low. For example, sodium chloride dissolves about 360 grams per liter, whereas calcium carbonate only 0.01 gram per liter. So on that basis, we thought that the degree of ionicity, all inorganic compounds were thought to be bound by ionic bonding. But later on, the theories on inorganic chemistry came that there can be a combination of that. It can be completely ionic or partially ionic or completely covalent. So the degree of ionicity determines the reaction of water molecules with the clay. So we saturated pure clay, pentonite clay with different cations like lithium, sodium, potassium, magnesium, calcium, barium. The samples, after saturating, they were washed and then dispersed. Now you can see that we also calculated the ionicity index by using this formula. That is, this is the ratio, IZ is the ratio of, this is the ratio of ionic potential at a particular valency compared to when the valency changes from Z to +1, what is the ionic potential. This ionic potential ratio determines how these ions are bonded to the clay, whether covalently or ionic, or the degree of ionicity I call is from that. If you say the ionicity index and the relative turbidity of this clay, even Adbray soil clay, you can have a very good correlation. So we thought that the ionicity of clay cation bonding is important in the dispersive reactions. Now, this is another example to say the same soil saturated with the calcium or magnesium or potassium or sodium, and the turbidity was measured and the zeta potential of the dispersed clay was also measured. You can see the calcium has very low zeta potential and also very low turbidity. The calcium, here I want to emphasize this experiment was done on a mechanically dispersed sample, not a spontaneous dispersion. So the calcium also dispersed, but it flocculates quickly. But the turbidity was very low compared to magnesium, then potassium is slightly more and sodium is the highest. Same thing in terms of zeta potential of the dispersed clay. So the hydration charge changes with the nature of the cation. Now, this is just to explain, when you have a dry soil which is bound together, all the silt, clay and everything is bound together as an aggregate, and at the stage when it is dry, the attractive forces are in megapascal, and the hydration reaction takes place with water molecules. It goes up to the stage of 2, swelling and slaking. Calcium and magnesium soils usually swell and slaking. There is a hydration reaction in for calcium clays and magnesium clays. And then after the stage 2, if it is monovalent cations like sodium and potassium, the continuous hydration takes place to the stage of dispersion. Or at the stage of swelling and slaking, that when the attractive forces between the particles in kilopascal, you can separate them by mechanical separation. That's where the rainfall impact comes. The rainfall impact comes at the stage when already the soils have reacted and gone to the stage of swelling and slaking, and then the mechanical separation takes place because of either cultivation or mechanical shaking or rainfall impact and so on. Now, going back to that is the flocculation. When you add the flocculating levels of concentration of cations or some other flocculating agents, then there is a osmotic dehydration, and the chemical bonding helps in the terms of bringing the particles together and making them as aggregates. On the basis of the ionicity index, we also thought that flocculating and dispersing powers are different. Even though the degree of ionicity is an indication of hydration reaction, the dispersion takes place on the basis of dispersive power of the cations, and the flocculation takes place on the basis of flocculating power of cations. Of course, flocculating power takes care of the valency factor that is derived from Schulz-Hardy rule, where they found that the dispersion or flocculation takes place according to the valency raised to the power of 4 or 3. When we use this formula and then we derive this flocculating power, and the dispersive power is just the inverse of the flocculating power, this is all compared to keeping sodium as a relation. In relation to sodium, the dispersive power, in relation to sodium, the flocculating power. And the values are given here anyway. The sodium, potassium, magnesium, calcium. Calcium is 45 times more flocculating as sodium. For example, to flocculate a soil, if you require 1 milliequivalent of calcium, you require 45 milliequivalents of sodium salt to flocculate. The other way in terms of dispersive power. Now, on this basis, we produce this new paradigm. Now, the soil aggregates, the clays and the organic matter produces the charge, positive charge or negative charge, mostly negative charge in Australian soils. This charge, the inherent charge of the clay minerals because of isomorphous substitution or edge charges on the basis of pH, they can be modified by combination with the different compounds like organic matter and so on. So the net hydration charge is because of how these molecules and compounds are interacting with each other. Now, after that, the charge, if it is a negative charge, it has to be balanced by the cations. The cations usually commonly found in soils are sodium, potassium, magnesium, and calcium. And on the basis of the dispersive power of the cations, exchangeable cations, the 45 times sodium plus 25 times potassium, 1.7 times magnesium and calcium as 1. Here the concentrations are exchangeable cations in terms of millimole charge per 100 gram or whatever. When the flocculating charge is in the solution, if you have a soil solution, it has salts. It can be very low or very high. But it is not on the basis of electrical conductivity we usually measure in terms of salinity, 1 decisiemens. It is the composition of the cations in the soil solution that determine the flocculation. So on the basis of the flocculation power of individual cations, you can calculate the flocculating charge if you know the concentration of soluble cations in milliequivalents per liter. Then when the dispersive charge calculated is equal to flocculating charge, it is called point of zero dispersion. There is no dispersion. If the dispersive charge is equal to flocculating charge, then there is no dispersion. But if dispersive charge is more than flocculating charge, then dispersion occurs. Therefore, the effect of different cations and dispersion is indirectly opposed by the flocculating power of the soluble cations. So dispersive charge minus flocculating charge gives the net dispersive charge, which is related to the amount of dispersed clay. Now, this is on this base. You have a dispersive charge. If you have increased, as the dispersive charge increases, percentage of clay dispersed increases. But if you increase the flocculating charge, just opposes, it becomes non-dispersive, flocculated. For a particular value of a dispersive charge, there is a particular value of flocculating charge where the dispersion is 0, which I call as point of zero dispersion, just like point of zero charge in the soil pH in relation to the charges. The point of zero charge is similar to the threshold electrolytic concentration developed by Quick and Schofield and followed by us long back, where we used to relate this ESP, exchangeable sodium percentage, and dispersion, and then find out what is the threshold electrolytic concentration. But now this concept is completely based on dispersive charge and flocculating charge, so this gives point of zero dispersion. The one idea came to me before, just when I was thinking about this slide. The point of zero dispersion is an important thing where if you can't measure dispersive charge, which exchangeable cation analysis is very tedious and so on, if you do the flocculation test, take a dispersed suspension, add some flocculating salts like calcium chloride or something, and flocculate to the level of zero dispersion, then estimate the cation concentration in the solution, and then calculate the flocculating charge, then that should be equal to dispersive charge. Now, when this hypothesis I was just proposing, I was discussing with Jack earlier, 2 months ago, and then I had a chance, the carbon project by Glenn McDonald, they had collected about hundreds of soil samples from all over southern Australia, from different depths and different types of soils and so on. They had analyzed for exchangeable cations. Then he gave me, what will you do with this data on exchangeable cations? Immediately it occurred to me, why can't we do the dispersion test? So I did the dispersion test, and I dispersed the clay. The net dispersive charge was calculated on the basis of exchangeable cations and the soluble cations in the soil solution. The correlation was very high. It is R-squared value was 0.77. In spite of the fact, if we had done exchangeable cations at the pH value of the soil, it would have been more accurate. Usually the exchangeable cation is done by ammonium chloride method around pH 7 or so, whereas the soils, all these 100 soils, the pH varied from 6 to 9.8. So that's one drawback in this, that we are trying to estimate the exchangeable cations at the pH value of the soil, then the correlation would have been very high. But anyway, it gives a very good encouragement to prove the hypothesis that dispersive charge is responsible for dispersion, and the net dispersive charge is related to the dispersed clay. Another interesting thing is, I went back to the original data of Emerson and Baker, who first proposed that sodium magnesium soil disperse more than sodium calcium soils. So I used the data that they gave ESP value and magnesium, exchangeable magnesium percentage, exchangeable calcium percentage, and so on for their soils. And they had also given cation exchanging capacity, so converted them into milliequivalents per 100 gram or millimole charge per 100 gram, and then used the dispersive charge, and then the solution concentration, they had given some data on very low value of salt, reduced that and calculated the net dispersive charge, and the dispersed clay was measured by them. So the correlation is 0.87. Therefore, there are two things from this. What Emerson and Baker told is correct, and also the factor I used for magnesium is also correct. I used the factor of 1.7 for magnesium. In fact, there is another paper by Curtin et al. They came to a conclusion that the dispersive power of magnesium is 4% that of sodium. When I use my factor of 1.7, it comes to 3.9%. So it's almost equal. So this gives me encouragement, and we will do more work to work out the calculation of dispersive charge on the basis of flocculation experiments, where flocculating charge can be calculated and whether it represents a dispersive charge. Now, on the basis of this, we can classify the soils, sodic soil, this and that, and nothing. Now it's simply dispersive soils with a different pH. The dispersive soil with pH neutral, alkaline, and highly alkaline, because the pH is an important factor in affecting crop productivity in terms of nutrient deficiency and toxic effects of aluminum and so manganese and iron and so on. There are saline dispersive soil, saline soil. This is what we have proposed for the new GRDC investment on dispersive soils, where there is an argument about sodium effect of magnesium and so on. I simply say that you measure dispersion irrespective of sodium or magnesium or potassium, then find out the pH and find out the EC, then you can classify and then make your management decisions. Now, this new paradigm gives a simple way of managing the soils. We don't worry about what is the exchangeable cation composition. You don't worry about what is the clay mineralogy. Don't be worried. Clay mineralogy indirectly worries, but we don't worry in terms of management. Then we don't worry about organic matter affecting this and that. What is important is you have to reduce the dispersive charge. This can be done by increasing the covalent bonding of cations, usually the low dispersive power cations like calcium and magnesium, which is more bound to the clays by covalent bonding, or any other new innovative amendments you can think of, which will reduce the dispersive charge, or by hydrophobic coverage of the charged clay particles, or by inner sphere completion by hydrolysis products of iron and aluminum. This was the first work when I joined here as a postdoc fellow with Malcolm Oates, where the iron and aluminum hydrolysis can reduce the swelling and dispersion. At that time, we didn't know the mechanism, but it is by inner sphere complexation where your hydration charge or the dispersive charge is reduced. Potassium can help in some clays. Potassium in some clays can be fixed by inner sphere complexation, potassium fixation. Only exchangeable potassium causes the dispersion problem and not the fixed potassium. Either you can do dispersive, reduce the dispersive charge, or increase the flocculating charge by increasing the concentration of cations of high flocculating powers. If you use low flocculating power cation, you have to use the concentration very high, which will increase the osmotic potential and affect the crop growth. Now, this is an area in the York Peninsula where Jim Kelly and we had experiment in for 4 years, and then the soil was originally highly dispersive. At the end of the experiment, we had very good crop production, and when I measured recently, the dispersive charge was reduced by 1/4 by applying gypsum and organic matter, biology, whatever happens there. Thank you.
A couple of questions for Renga? Ron,
so you've got the four main cations there, and you're assessing them according to their ionic charge. What about in acidic soils? You've got aluminium. Is that
Yes.
Where does that fit within the scale? And what about ammonium?
Yeah, usually that's one area we have to work on aluminium, because in the case of acidic soils, exchangeable aluminium can be more. There are sodic soils in New South Wales which are acidic with pH about between 4 and 6, 4 and 5.5, and they say they disperse. I was first wondering why exchangeable aluminium is so thin and aluminium flocculates and so on. So I'll have to work, but most of the exchangeable aluminum concentration is so low. So most of the soils I used was pH above 6, but I asked people in New South Wales to give me some acidic soils to work out the flocculating power of aluminum or dispersive power of aluminum. You are right, aluminum can also come in. Yep.
What would be some of the practical ways, in your experience, that
Yeah. The common thing is usually for sodic soils, they use mostly gypsum. Gypsum is calcium sulfate. Gypsum, in terms of the gypsum, it can also remove the sodium from the exchange complex, and then calcium can enter into the exchange complex. So when calcium enters into the exchange complex, it's more covalently bonded, so the dispersive charge is decreased a lot. Even in the potassium soils, gypsum can replace. Even in magnesium soil, calcium can replace. So therefore, irrespective of the exchangeable cation causing this dispersion, like sodium, potassium, or magnesium, calcium can also cause some cases swelling problem and so on. So to maximize the reduction in dispersive charge, we have to choose a cation which is having more covalent, less ionicity, and high flocculating power, or less dispersive power. That's the usual thing. The other one is organic matter again. If the organic matter is, not the fresh organic matter, but as a humification takes place, the organic matter also can covalently bond to the clay, reduce the dispersive charge. And there is hydrophobic effect. They are using different organic polymers, polyvinyl alcohol and so on, which polyacrylamide, which can also cover the dispersive charge, but because the molecules being hydrophobic, they don't react with water. But the cost, it all comes into the cost. They are using organic polymers will be very costly for dryland farming. Very specialized farming with high income, you can use that. Israelis have tried this in their horticultural enterprises. Yep.
And just to follow on, those hydroponic polymers, they're not going to cause any issues with non-wetting or anything?
Yes, it can. It can. For example, non-wetting soils are because of the hydrophobic nature of the fungal materials and cost covering the sandy soils. It can cost, but you have to adjust according to not to the level of non-wetting. If you have a little bit of dispersive charge, high dispersive charge is reduced to a low level, still it will wet, but at the same time dispersion is reduced. The other future research should see clay dispersion takes place. We don't know how much clay will affect the actual soil physical properties to a level of hindering crop production. For example, if you have a 1% clay dispersion may affect a clay soil very much, but in a sandy soil it may not affect that much. So this is the future research is needed to quantify how much clay will, for different types of soil, how much clay is important as a critical value, above which and below which you have to take them.
Any other follow-up questions?
Get on.
Have you thought about how this may be related to pedology, particularly clay alluviation? Can it be understood in that kind of context that in the topsoil you've got net dispersive conditions, and in the subsoil net flocculation? Is that?
I think that the alluviation, that's why the formation of duplex soils here, because of the clay migrating downwards and like that. But once the clay starts accumulating in the teething, then there is no further hydraulic movement and clay. That's why we have dense subsoil clays everywhere. But we are in this one, we are looking at how the dispersion occurs, the mechanism of dispersion occurs, how it can be reduced in terms of crop production. But in terms of pedology, it can be useful. I didn't think about pedological thing like soil characterization or profile characterization on the basis of morphology and so on.
I think that's it. Yeah. Thank you, Ranga. Thanks for hanging around so it'd be good to catch up with everyone. Just take this opportunity again to congratulate Ranga and Jeff on the respective awards with great achievement. So thank you too for giving us the presentation. Thanks, Ranga. Yeah, catch us for the next event, which should be a soil classification workshop coming up in early October, I think. But keep your ears peeled. But thanks for coming again.